Hello, my name is Devin Patel. I did my project over predicting party affiliation of Twitter statuses using sentiment analysis and popularity metrics. The social media platforms are taking a further integrated place in society. A lot of people are more spending time online, which attracts a lot of public figures to build their platform on these social media sites, particularly politicians. So this study will focus on Twitter in particular and determining how reliant these politicians of different parties are on using strong language and other sensationalist emotional persuasion on their accounts. To begin this line of questioning, a correlation must be determined between party affiliation and sentiment analysis metrics of their Twitter statuses. This also takes into consideration whether popular tweets use stronger language. So sentiment analysis is the scoring of sentences and phrases based on the opinion expressed in those sentences and phrases. The two metrics for sentiment analysis are usually subjectivity and polarity. Subjectivity is how opinionated the text is, with 0 being a non-existent or cold opinion and 1 being a strong or hot opinion. Polarity is the direction the opinion is going in. Its values are -1, which is a very negative opinion. They use words like hate, kill, or death. 0 are very neutral words. They're like your standard the, and them words. And 1 indicates very strong, extremely positive opinions. Words like help or love. Now, to create these scores, I will use the open source natural language processor TextBlob generator. In order to perform sentiment analysis on the tweets, we need to be able to fetch them. Twitter supports a Python API where registered developers can freely pull from Twitter's database. Pictured in the slide is the developer dashboard. Twitter walks through the authentication process, and I'll demonstrate how this works in the demo. So we need a collection of tweets to analyze. So I used the dataset from Harvard database. This set contains thousands of tweet IDs related to the 2016 presidential election, all organized by party. So 62,952 total tweets were pulled, and the breakdown of which are in the table. The Democratic candidate timelines comes from Hillary Clinton's official Twitter account. The Republican one came from Donald Trump's official account, and the Democratic Party and Republican Party IDs both come from various Democratic and Republican accounts during this time period. So of course all this has to be compiled. So each tweet collects the number of likes and retweets. This can come from the TweetPy API, and the subjectivity and polarity scores are generated from TextBlob. To store the data, it will be exported as a binary pickle file for easy and lightweight unpacking, and as a CSV for a more viewable output. After this is done, we're ready for analysis. So let's look at the correlation matrix first. So retweets and likes are highly correlated, which makes sense since more likes means more people saw and supported it, and that would lead to more retweets and vice versa. However, in scatter plots on the right, the plot with subjectivity and likes seems to be independent of each other. This is also true for polarity and likes, as well as any combination of likes or retweets with subjectivity or polarity. Using likes and retweets in conjunction with subjectivity or polarity seem to be the best approach to analyze this data, so both sets will be tested in the study. There will be one wave where likes, retweets, and subjectivity will be tested, and another wave where likes, retweets, and polarity will be tested. So the 3 feature selection methods used were PCA, LDA, and analysis of variance, which is ANOVA. So PCA is reorganizing features according to maximum variance. LDA is maximizing between class scatter and minimizing within class scatter. Analysis of variance analyzes a variation in a continuous variable measured under discrete factors. It's particularly useful for the continuous sentiment metrics. Now, LDA, the plots I'm about to show you, LDA can only reduce to one class because there are only one feature because there are 2 classes. So I cannot really make an effective plot, and I have LDA turned out to be the worst performing feature selection method. So PCA, on the left, is the data set without polarity. So it's likes, retweets, and subjectivity. The explained variance ratio of it is 99.93%, which means the most varied component includes about 99.93% of the variation, which is very high. And the explain variance ratio with the drop subjectivity or with polarity is 99.7%. So because of this, I'm expecting a little bit more favorability to the polarity or to the subjectivity, and because it has a little bit more separability than the polarity. So for move on to ANOVA, ANOVA is more successful in separating the classes. So at this point, I was expecting ANOVA to perform better than PCA and LDA. There's a bit more separation between the classes, and I'm expecting it to perform way much better than PCA. So the classifiers I used were Gaussian naive Bayes, support vector machines with RBF kernel, and I'm using sklearn's MLP convolution neural network. Each classifier is tested on a training set sizes 10%, 20%, 30%, 40%, and 50%. So the accuracy plots for PCA reduced datasets are in this slide. This on the left is with subjectivity, on the right is with polarity. MLP performed the best, roughly 64 to 65% accuracy across all training sets, while the others hung, Gaussian, naive Bayes, and SVM hung around 52 or 54%. For LDA, it performed the worst. The MLP stooped down to roughly 54% to 55%, and this is largely, again, due to LDA reducing down to one feature, which is eliminating a lot of important data. ANOVA saw some of the best results, with Gaussian naive Bayes performing well without polarity at 55 to 56%. SVM stays steady at 54%. MLP went as far as up to 68% and averages out at 66% accuracy for both subjectivity and polarity. So here's the confusion matrix to get the sensitivity and specificity scores for each classifier. I had to choose I chose the best method of classification to present. The other confusion matrices and sensitivity specificity tables are available in the report in Appendix A, but for the sake of conciseness, I chose to stick with ANOVA reduced dropped MLP classified confusion matrix. So drop polarity got a high sensitivity score for Republican, and Democrat classifications just got over half that score. There's the drop subjectivity had a slightly worse sensitivity score for both Republican and, well, slightly worse sensitivity score for Democrat. Now, what these confusion matrices convey is that the strength of the words, or the subjectivity, is more correlated with political parties than polarity. So the goal of the project is to determine a correlation between sentiment matrix and the political parties on Twitter statuses. Based on statuses from both parties and their respective candidates, the results from the study suggest that subjectivity is more correlated to party affiliation than polarity. This is true across all statuses, regardless of popularity metrics, meaning that more likes and retweets have no effect on the content of the text. Now, there is promising evidence to suggest that a correlation between sentence structure, word choice, and party affiliation, and if the correlation is proven, the results of this can be used to analyze political party publicity and outline the emotional persuasion tactics these parties use on social media. Now, some important consideration to note is that the content of the statuses themselves tend to be more neutral. These are professional public figures accounts, so a lot of their statuses came out to zero subjectivity and zero polarity. In addition, the sentiment analysis tool used can be misled as well. Take for instance the sentence, "It is horrifying and unacceptable to allow hate to spread in this community." Horrifying, unacceptable, and hate would give it negative polarity scores, even though the message as a whole comes from a place of positivity. Sarcasm and figurative language are also not accounted for very well because of this. So further avenues of study is to also include some of the replies and comments of the statuses, as they still reflect the initial political party while not having the same professionalism. We may see more opinionated statuses from there. It can also contribute to the popularity metrics as well. Another avenue of study is to further dissect the sentence structure of every tweet. Does one party use more of an active voice than the other? Does one party use more descriptive words, like adverbs and adjectives, than the other? And so on. Right, these are the references I use for both the projects in the slide. And now we move on to the demo. This is the demo of my code. As you can see here, this is the data gathering stage. It's where it reads in tweets and pulls them from TweetPy. So just to give you an idea of what the data looks like, they're all text files with a list of Twitter IDs, some initialization, importing text blob, and TweetPy. TweetPy also requires that you need to authenticate it, so this is what this function does. We're going to be pulling 20,000 tweets, which like 20,000 of these IDs pretty much. So this function actually pulls the statuses, it makes the API calls, it returns all the statuses, all the IDs that went through, as well as any statuses that failed, and that's for logging purposes. It gets put into the logs folder. So after that is done, it gets put through collect statuses, which gets all the different features of the data. It compiles the text, the number of likes, which TweetPy calls favorites, the retweet data, and which party they belong to. So after that is done, it makes a data frame with all the relevant data and a text data frame for the sentiment analysis. So after that, we are ready for sentiment analysis. First, we have to clean the text, so we need to remove any at mentions that are in the text, as well as any hashtag symbols, any hyperlinks, and other things like that. So after that is done, we can generate the scores, which this function generates a sentiment subjectivity score. This one gets the polarity score. And once that's collected, this is what the final data frame looks like. And it gets exported as a CSV down here. This is what the CSV looks like. So we have all the different data frame headers, and we have a text in addition to it. After we are done with pre-processing, we move on to feature selection, and we are going to be performing PCA, LDA, and ANOVA, which is these two. We are also going to normalize the data using min-max scale. So this is the export function to create the figure images. This is the loading in the data. Reads it from the pickle file, normalizes it, and gets all the. It also drops the subjectivity and polarity, so it creates two separate data frames. Once that is done, it prints out the shape and moves on to the correlation matrix. This is exactly how it was done in the homework. Creates the heat map correlation matrix, and it's displayed here. It's also exported as a figure. Same with the lower C matrix, and this is the whole complete scatter plot of all the features. Then we move on to PCA, which this cell creates the explained variance ratio of each component. As you can see, this is the 99.93%, and this is the 99.7%. So the PCA components go through, this is creating the plots. So this is comparing subjectivity and polarity, with separating the two colors so you can see them clearly. And this is them overlaid on top of each other. And this is sent to drop polarity. So this is subjectivity on the bottom. This is polarity on the bottom. LDA, again, there's no plot because there's only two classes. They can only reduce down to one dimension, so there is no plot that can be made with one dimension. ANOVA is the same process. This creates the new data sets, and they get plotted below with one plot with the separate classes, so you can see individual class basis, and one with it overlaid onto each other. Right, and moving on to the classifiers, we initialize the classifiers. We are using Gaussian naive Bayes, SVM with RBF kernel, and the MLP classifier. And this is where we create the classification accuracies. So first, we need a performance evaluation, which is what this does. It's a box and whisker plot. It's this figure right here, just to get an idea of how accurate each classifier is going to be before actually committing to the accuracy plots. So this is for PCA, without polarity, without subjectivity, and this is, let's see, PCA without polarity. These are the accuracy plots. Again, this is the same code that we had in homework 4. And confusion matrices, it's done with the sklearn's confusion matrix display, and it uses a pipeline estimator to do this. So it's ran through. Again, same function for used in the homework. It creates the confusion matrix, and then it calculates the sensitivity and specificity. of that table, and it creates it creates the table and plots it to there. Again, this is a function, so it's going to be the same code for all three of the methods. This is PCA. It creates it for Gaussian naive Bayes, SVM-RBF, and MLP. And this is the for dropped subjectivity or just polarity. So same thing, Gaussian naive Bayes, SVM, and MLP. And that is it for the demo. That is all the code. Great. Thank you for watching.